I just want to start with the beginning, Helen, because as far as I understand, in your upbringing, you had the ability to ask a ton of questions, and you also had parents who supported you in the pursuit of finding the answers to all your questions. Was that like the main topic growing up, that you just had this curiosity?
The thing about the part of the northwest of England where I come from, so I grew up just south of Manchester, which was obviously a big industrial town. And, in the early industrial revolution, it happened there first. And so people around there are very pragmatic and they're interested in technical things. There's a lot of technical industries. So asking questions wasn't really it wasn't just my family, it was that people weren't afraid to find out. There were libraries and there were ways you could go and explore things, and there was this sort of attitude of just, oh well, let's go, let's have a go. No one took themselves very seriously. It feels like now perhaps everyone's much more career minded, and there's this question of, what's in it for me, and should I do this, and will it go on my CV? And the attitude I remember growing up was just, well, we're just ordinary people, and here are, we just have the opportunity. The asking question, trying to understand is part of it, but it's not a defining part of everyone's identity. It's just, oh well, let's go to the library and find out. That's what the library's there for.
Yeah.
um, and it's okay to take the time to do that. It's okay to take the time to be curious just because it's interesting, not because it's going to get you a certificate or anything else. And of course you have a lot of freedom with that. And actually my friends who live there now, watching them bring up their children, it's actually very similar, that there's just lots of ideas around, but it's not a big thing. It's not, people don't talk about it. It's just, it underlies what everyone does because they're very pragmatic. In that part of the world, you had to just get on with it, as they would say. You just had to, you know, make everything work and not make a fuss about it. And so they do. And that's what
Yeah.
I grew up with.
Yeah, but so how early will you say it's sort of the science then piqued your interest? Because you can be curious about a lot of things, how a machine works, you want to work in a factory, but still the route you took is a bit more technical, I would dare to claim.
I was always interested in how things worked. And I read a lot, and I did a lot of other things, but I guess, I mean, my parents were both on the science end of things. My dad was a polymer technologist, so he worked for BASF. So, he was bringing home plastic samples and talking about that. And my mum is good at maths. And so I remember her teaching me maths. There was a blackboard in the kitchen, and she would teach me maths. And so I guess that part of how it worked came from them. But I do know. So when you're in Britain at the age of 14, you choose some exams. You choose which subjects you're going to sit. And I did something very unusual. So there was so there were sort of 9 subjects, and you could either take 3 of them to do science, or you could take 2 of them to do science. And everybody expected me to take 3, and I took 2 because then I could do another subject then I could do something else. Then I could study history because I knew I was going to do science. So even at 14, it was obvious to me that I was going to be a scientist because I took the opportunity. Oh, I should study history now because I'm not going to be able to sit in classes on that after this in the same way. So I don't really remember, but the scientific background was always there. And of course, my family was technical. My grandfather had been one of the first television engineers. So that was the environment I was in, I guess.
Did you have any heroes growing up? Because one of my favorite scientists from UK is Michael Faraday, and I just feel like his story is incredible on how he started from basically nothing and ended up becoming one of the most influential people of his time. And I saw you also did the legendary Christmas lecture that I think it was like the start, was his idea or something. So has that been a person that influenced you, or did you have other people who inspired you to pursue science? Because it's a lot of work in the end, and if you want to do important work, you have to spend a lot of time on it, of course.
Yeah, so Faraday, I think he did start the Christmas lectures, and he gave them for many years. So now it's a different person every year, but he gave them successively for many years. And his most famous one, I think, was on the science of a candle. And he spent the whole lecture talking about all the things they knew about the candles in the early 1800s. I have never had heroes. I don't operate like that. I get asked that question a lot, and I don't. I think there's a lot of things people say because they're expected to say them, and we have an expectation that people have heroes. And there are plenty of people I respect, and Faraday, of course, is one of them. But I've never looked at people and wanted to be somebody else. I think there's lots of people that do brilliant stuff, and that is great. But I've never had, there's never been someone who I have really become obsessed with, or have spent a lot of time thinking about. But I mean, and of course, some of the interesting ones have been explorers, and Nansen is a good example of someone who did many things with his life and who I have great admiration for. And I've visited the Fram and I love it. But yeah, no, heroes, I think not, it's probably just as well that I didn't want heroes, because there weren't any that looked like me. Like a girl from the north of England was not what anybody's heroes looked like. And so actually, I think not having that mindset was probably very helpful to me, because I didn't worry about being anybody else or doing, I did lots of things that I wasn't expected to do. I went and tried things. And at the age of like 13, I was building dry stone walls, these traditional walls around Britain. What 13-year-old does that, right? But I wasn't thinking about myself in terms of anybody else. I was just, oh, well, that's interesting. I'll go and try that. And so I would love to know how common this is in the population, not to really respond to the hero thing, and whether I'm just a freak of some sort. But I think it's very useful not to have heroes, and not to, because people talk about role models. And of course, we know the evidence shows that role models are very expensive, especially for important, especially for women. But isn't it useful not to need a role model? Because then you can just do what you want to do. You don't have to look for someone else who's done it first. So no heroes. Sorry.
Yeah. No, but I think that's an excellent point, because maybe you then are more open to carve out your own way. And I think, doing this research, I saw this fantastic video of you in the US many, many years ago discussing or giving a breakdown into bubbles in the ocean. And I was like, wow, to be that interested in bubbles, like there was no person that pointed you in that direction. Maybe it's, from my point, you found that thing and you just doubled down on it. So is that just one example on how you find a topic and really drove down to understand the bubbles in particular?
I think I don't take myself very seriously, in a sense. Like, the thing that drives me is curiosity and ideas, and I'm very neutral about what those ideas are, if you like. I think curiosity is a very broad thing, and I think there's of course, there's lots, there's sort of two reasons for there's two ways you can think about science. You can think about it as a tool. So we're going to learn about how viruses work so that we can create vaccinations, so that we can stop pandemics, right? That sort of thing. And of course, that's very important. But we can also value ideas just because curiosity is the most human thing there is. And when you look at, we can define ourselves as a species in very many ways. We're very social. We have a lot of manual dexterity. We can build things and do things. We can make clothes instead of needing fur. We can create that sort of thing for ourselves. But really, human curiosity is the thing that is at the root of all of it. Because if you have curiosity, then you experiment with making clothes, and then you experiment with organizing your social group differently, and somebody goes out of the group to go exploring over the next mountain. And so I think curiosity for its own sake is a very powerful thing. And we live in a world which is very it's very transactional. If I do this, what happens next? And the thing about human curiosity is there doesn't have to be a what happens next. It's enough. You discover an amazing thing about the world. Like, you discover that there's some kind of worm that has a completely crazy life cycle, and you read about the worm for 2 hours, and it's really interesting, and that is worth it all by itself. And of course, in the big picture, later on, that knowledge is going to become useful somewhere, that you've then got a very rich environment to draw on when you're thinking of new ideas. But you didn't do it because you thought you were going to have an idea because of it. You did it just because it was interesting. And, there's a place for that kind of curiosity. And so I'm very, I'm interested in interesting things, but I am most interested, it's true, in how things work. Like, I'm not satisfied with superficial explanations. I want to know on a deeper level how things work, which is how I ended up with physics, because that's the thing, like the most basic mechanics of the universe. It's written in the physical laws. And so I do have I mean, I want to go deep enough to know I have the fundamentals. But yeah, no, I think having curiosity for its own sake is, and the fun that you get out of curiosity and the fun that you get out of satisfying curiosity, I think is often underappreciated. You know, there was a talk I gave a few years ago where, and I was talking to business people actually, it's not the sort of audience I normally speak to. And I had slightly run out of time at the end of my talk. And so I had this demonstration, and you can try this at home. If you get a raw egg and a boiled egg, both in their shells, and you sit them on the table in front of you cold, you know, so they look the same. And if you on their side, and if you spin them round on their side, they start spinning, and that's fine. And then if you just put your finger on the top very quickly and then take it away, and you do that to both eggs, they'll do something different. And I'm not going to tell you what it is, because what happened at that event was I got to that point and then I kind of went, oh, I'm out of time. See if you can work it out for yourselves. And then I sort of finished. And then I went off stage and I had literally adult men tapping me on the shoulder going, is it this, is it this, is it this? You know, they'd had a think and they'd worked it out and they really wanted to know, and they really wanted, and they were so proud of themselves when they'd worked it out for themselves. And there's one side of that which is like, it's an egg spinning on the table, and of course it isn't, because the same physics that is driving that thing is also keeping satellites pointing the right direction in space, and it also makes a lot of big important things in the world work. But the joy on their faces when I told them they'd got it right was amazing. And I realized that they were going to remember it because they'd worked it out, because they'd had the joy of working it out. And so I'm not going to tell you what happens with the eggs, but, you know, take a boiled egg and a raw egg, spin them round, tap the top, have a play, and see if you can work out which one's raw and which one's boiled without taking the shell off. And you'll do it, and it'll be fun.
I think that's a great experience. So I hope the audience try it at home. So, but if we take the concept of, if you take yourself as an example and you want to dive into a complicated topic, because what I think happens is that people want to learn things, but if it's too difficult, they will probably give up in the end. So if you are trying to explore a new topic, do you have any ways of, you know, getting a framework or a way of doing it? Even it can be experiments like you just explained, in order to have that stamina to pursue it, because some of the topics are quite hard to understand at a fundamental level, which requires that you spend enough time learning it. But I think many just give up in the end.
Well, the thing that you have to remember about learning is that we learn by association, and that means when we need a framework to put something in. So I often say to scientists, you know, I was saying to some students yesterday that, you know, PhD students talking about their science, that when they're talking to other people, they see that they've got this very shiny decoration. It's like a shiny Christmas decoration, and they're really proud of it, and they're waving it at everybody, saying, look at my Christmas decoration, look at how shiny it is, isn't it pretty? And nobody cares, because nobody knows that Christmas trees exist, so they haven't got anywhere to put that nice little shiny thing. But as soon as you tell people about the Christmas tree, then they know what to do with your piece of information, you know, your new thing. And I think a lot of learning is like that. You have to see a bigger framework, a bigger shape that makes, and then when you learn the important thing at the bottom, you have somewhere to put it. You know where it belongs, and you're going to remember where it lives on that structure, and then you can see things in relation to each other. And so the habit of science, actually the habit of doing science, is the habit of finding Christmas trees, which I've never actually thought before quite that explicitly, but that's what we're doing. We see something weird, and then you go looking for the bigger structure behind the thing you saw. And so I guess I'm trained in finding Christmas trees. And when you're learning, that's what you're doing, right? You're sort of taking notes, and you're taking in information, and you're trying to put it all in a shape. How do these pieces of information fit together? And then when you get down to the details, you've got somewhere to put them. And so I guess as a scientist, I've got a lot of experience. I've got a lot of experience. I'm trained, I guess, in looking for information and looking for that framework first. If I don't have the framework, I've got nowhere to put the new stuff. And so that, and I think that is how to learn. You've got to look at, and the problem is that the thing when you're teaching or when you're communicating, it's the same in a presentation, is that you have to have done all the thinking to work out how the picture fits together for your audience, so that you present you draw the picture in the right order for them. You've got, and that is hard work. It's hard to really think about which ideas have priority and to put them in order so that when your audience gets their nice little Christmas decoration, they've got somewhere to put it. And so it's all that habit. And it's actually the same in science as it is in communication. It's about the prioritization of ideas and really seeing through to the core of something in order to be able to then take the 3 steps that get you from I don't know anything to why this is important. And I guess in the, you know, it's the same in the TV stuff. That's what you're doing. You're guiding people down that route. And so the TV and writing and science, it's all the same. It's the prioritization of ideas. You're doing the thinking to make it easier for the audience to slide down that chain of ideas. People don't often think that communication is hard work, but the important part of communication is the thinking you did before you started communicating. Yeah. And so, you know, it's that habit, I think, of how you of discipline with ideas.
Yeah. I think that's a great answer, and also maybe the perfect segue over to The Blue Machine, the book you've written about the ocean, because talking about Christmas trees, that's a huge one. So it's like, yeah. Where do you even start in trying to explain it? So what sparked the idea in giving the ocean a big book to explain the mechanics behind it? And yeah, how did you work on finding the right ideas to tackle in the book?
Well, I guess it came out of slight frustration. I mean, when it came to time to think of the topic for the next book I was going to write, you know, you think about a lot of things, and then I remembered that so I did my PhD in something else, in experimental explosives physics, a different type of physics, and after my PhD, I took a postdoc job at the Scripps Institution of Oceanography, and then I sort of discovered the ocean at the age of 26, and as soon as someone had pointed it out that the ocean was this physical, you know, they pointed out the physicality of the ocean, and I actually looked at it with physics in mind. I went, oh, I get it. I don't know anything, but I can see you know, now I've just seen a different perspective. I get it. There are things to know about this. And there was this period of like a couple of weeks where I thought this was amazing. And then I became very indignant. How is it? Like, I was that kid that read all the science books and all the science magazines and all the stuff I was supposed to. Nobody told me about the ocean. This is completely ridiculous. And I actually went around Scripps, which was a big oceanography institution, and I went towards the end of my postdoc there. I went around knocking on doors, and I asked the people behind the doors, like, I've just arrived in the world of the ocean. I don't know anything about it. Can you recommend me a book? And they did recommend a lot of books, and none of them were about the ocean, really. They were about the things in the ocean, or they were about other stuff, you know, other interesting things in the world. And I was very grateful. They were all very brilliant books. Not a single book really explained the physicality of the ocean to me. And so, you know, move forward 15 years, whatever it was, and I'm looking around for a topic for another book, and still no one has written this book. Still no one has said this is what the ocean is. And yet oceanographers know this. And so I had learned in bits and pieces along the way. You know, I'd studied the bubbles and the science that I was qualified in, and then at the same time I'd just gone to every lecture and every seminar, and I'd built up this picture, and I could see all these people saw this thing and they weren't telling the rest of the world about it, and so the rest of the world just thought the ocean was blue filler with fish in it, and it felt that was a big disconnect. You know, there's a massive story to tell here, and then of course you get to why it is no one's told that story, and it's because it's hard. And so what I did, and so I spent a long time, you know, my first book, my writing plan was literally 10 post-it notes stuck on a piece of card, and that was all, because the structure was very simple. And this one, I collected cards and ideas, and I was looking for things that connected together some aspect of how the physical nature of how the ocean worked with a human story or an animal story. And so I just collected ideas, and then I had to organize them. And so it just took a lot of thinking to work out how to organize all the bits and pieces. But fundamentally, it was like I had to go looking, because the oceanographers don't know the history and the historians don't know the oceanography. So there are very clear links, but you sort of have to go digging for them, even they're in plain sight, because nobody thinks about the world that way. So I had to do a lot of work to back up the ideas, just because no one else had done it. So I went looking for these small stories, because I think it's like there's an ancient story of the 3 blind men and the elephant, where three blind men somewhere come across an elephant, and one reaches out his hand and touches the leg and says, oh, it's like a tree, and one touches the trunk of the elephant and says, oh, an elephant is like a snake. And of course it's all true. It is true that the legs of an elephant are a bit like a tree, and it is true that the trunk of an elephant is a bit like a snake, but they're all partial truths. And so I think the way to see the ocean is to tell lots of these stories from different perspectives, different timescales, different size scales, different animals. And then when you put all the partial truths together, you have the picture of what the ocean is. And it's not simple to say what the ocean is, but by telling lots of these stories, then you can sort of see what the ocean is. And of course, that's the privilege of what you can do in a book. You can put together all the pictures that show the bigger story. And it's very cathartic, because now I can just say, read the book. If you don't know what the ocean is, read the book. I promise you will find it interesting, because you won't have looked at it like this before.
Yeah. I think I told you previously, but I found your book at the bookstore. I was just like walking around looking at different books. And I also think like the cover, it's not a coincidence you chose that cover. So maybe you can explain also why that photo, we can show it on YouTube, is very important, because it gives you a new perspective of ocean that you don't get on a typical map with countries in it.
So the great problem of looking at the ocean is that the ocean is on a spherical planet, and that means you can't see all of it at once. So of course, what we do with our maps of the land is we sort of unwrap the planet in different ways. And a guy in 1942, Athelstan Spilhaus, who was an interesting so-and-so, but anyway, interesting character. But he said, in order to see the land, we always cut the ocean. And so in order to see the ocean, we must cut the land. And that is the thing that humans never do. Right, they never cut the land, because that's the bit that's important to us on the surface of it. So he drew this map where he cut through the continents and unwrapped the globe so that you could see the whole ocean. And what you can see is that it's connected together, and it's called the Spilhaus projection. And it's sometimes you see it on social media. People say it's something like the world according to a fish, because what it shows is that all the world's oceans are connected, and that it's not that there are 5 oceans or 7 or whatever we get taught in geography class. It's one big engine. And then and what's the version that's on the front cover of the book also has some beautiful gold arrows that show where the major ocean currents go. And once you see it like that, you see not only is this thing connected, but that it's moving, and that the way, you can see it as an engine, which is what it is, a single connected engine, which is driving the way our planet works, because the ocean is the beating heart of planet Earth. It's not just, living on a blue planet is not about a color. It is entirely what defines planet Earth. The water in the ocean is the thing that makes us different from other planets, and that sets the environment that we live in lots and lots and lots of different ways, not just the big obvious ones. And so once you unwrap the map like that, you can start to appreciate it. And you can also perhaps start to appreciate how big the Pacific is, because it really is enormous. And we don't often, even if you just turn a globe around and you look from sort of over the top of Hawaii, all you can see is ocean. If the aliens came to visit and they came from that direction, they would think this is an entirely water world. So yeah, I think that perspective is very useful.
Definitely. So, how strong do you feel our knowledge base is about the ocean today? And I hate to bring up this analogy because I know it can be triggering, but you have also talking about the famous quote that we know more about planets than we do about the ocean, but that's the completely wrong way of looking at it. So, I just have to make you say that again.
Yeah, well, so it's normally the phrase goes, we know more about the moon than we know about the deep ocean, and it drives me nuts. And if to the people listening to this podcast, if you take one thing away from this, please never say that again, because it is wrong and it's misleading. And it came from a grain of truth. It came from the fact that back in the 60s, it was easy to map the shape of the surface of the moon, because you can use light and there's nothing covering it, so you just look at it. And someone said, we've mapped the moon to a better resolution than we have mapped all of the deep ocean, which was true, because we can't see through the ocean with light in the way that we can see, just look at the moon. And so the problem is that became interpreted in a different way, that we know more about the moon than we know about the ocean. And of course, that is not true, because the ocean is not like the moon. It's got 3 dimensions. It's full of lots of life. It's got all kinds of interesting geology and chemistry. It's dynamic. It's changing. The moon literally has not changed in 2 billion years, apart from where the Apollo astronauts went and, left some stuff and brought some other stuff back. I don't have anything against the moon, but it is a dead rock. And the ocean is a dynamic, living place with these amazing subtleties and complexities. And so there's huge amounts more to know about the ocean. And of course, thousands and thousands of oceanographers have been learning things about the ocean. 12 men have walked on the moon. Thousands of people have been to sea and have learned about the ocean and have written about it. There's no question that we know far, far more about the ocean than we know about the moon, because there's more to know. And the biggest problem with the comparison is that every time we compare the deep ocean to the moon, we are conveying the idea that they are equivalent, that the deep ocean is equivalent to a bare dead rock that hasn't changed in 2 billion years. And that is not true. It is a much richer environment than that. And so, of course, we know more about the ocean than we know about the moon by many, many orders of magnitude, because there's much, much more to know. But of course, we still have much more to discover, because we're only just at the start of this journey. So there's plenty of ocean discovery still to go, but we definitely know more about the ocean than we know about the moon. That's the short version of the rant.
Yeah, I think, and one insight I learned from you is that, humans are quite visual. So we like to observe things with our eyes, but you have perfectly explained that, in the ocean, there are, things like sounds is like one of the main things to study. So can you also explain a bit that thing? Because that also gets to, like, maybe if you see a photo at the moon, that's very visual, but in the ocean, it's not necessarily the eyes that's going to do the research all the time.
Yeah, although I would point out that actually the most important photos taken on the Apollo missions were of the Earth. Everybody thinks those missions were about going to the moon. And that was only the excuse that made us turn around and look at the planet Earth, So there's no question that the most important photos that came from those missions are of Earth, not of the moon. And how silly that we had to go all the way there to look back here. But anyway, what did you ask me about?
Sounds in the ocean.
Sounds, yeah, right. So we get information from a long way away via something has to travel, right, to get from there to here. And on land, as in the ocean, there are 2 major messengers. There's light and there's sound. And on land, we completely take for granted that light is the long distance messenger. We can see the moon, we can see mountains that are a long distance away, we can see our friend on the other side of the town square. But we also take it for granted that we can't hear our friend on the other side of the town square. Sound doesn't actually travel very well through air. So we can't hear things that are a long way away in general, unless they're very, very loud. So sound is a short distance messenger for us. And light is the long distance messenger. But in the ocean, it's the other way around. Light is absorbed relatively quickly, even in the clearest waters within a couple of 100 meters. But sound in the right conditions can travel a very, very long way. So sound is the long distance messenger in the ocean. But then the tragedy of that is that if we look down, we are visual creatures, as you said. If we look down into the ocean, because light doesn't go very far, we don't see very much, we just see darkness. And so it's not the case that you can just illuminate the ocean with a big light and then take a photo of it, because the light just doesn't go very far. So we have to take our pictures of the ocean with sound, but that requires, special machinery, and it requires reconstructing images, and that's not how our minds work. So because the fact that light is absorbed in the top few meters of the ocean actually defines how the ocean, it's one of the very important things about the ocean engine, because when the light is taken away, that energy becomes heat. And so the sunlight heats up the top layer of the ocean, which is very important. But the fact that it means that we can't look into the ocean the way that we look into the sky and see the different layers and the different things happening at different depths. I mean, it's probably very good for the fish, because if we could see all the fish, we would have fished them out far earlier. But that there's a kind of tragedy there, that because it doesn't fit our priorities, it has become invisible to us. And so we miss the greatest story on Earth, because we insist on only seeing, the things that our own eyes tell us. But of course, now we have technology that helps us out, and it's time to revise that view a bit.
what has been some of your favorite expeditions? Because I know you've been on a ton of different research vessels and been all around the world. Do you have any particular memories that really struck your mind and was impressive?
Yeah, so working out at sea is a privilege because you get to see you feel very small in a very big ocean. And most of what I do is open ocean research. So it's not like the North Sea. I have worked in the North Sea and the Baltic, but they are, they're kind of crowded seas. There's ships all the time. There's lots of structures. There's always something. You can always see something from a ship in either the Baltic Sea or the North Sea. Whereas out on the open ocean, you don't see anything. You don't see other ships very often. You don't see, there's no structures, there's no land. You're just very small within the ocean, which is very good for humility. One of the nice things about ocean scientists is that they have to have quite a lot of humility because the ocean will, you're not in control. It will come and do unexpected things, and you have to deal with that. And it makes oceanographers very nice people because they can't be arrogant, because the ocean will always come up and slap you, basically. So you have to learn to deal with that. So yeah, I guess maybe some of the more memorable expeditions. I mean, I've been to the North Pole on a Swedish icebreaker, the Udin, and that was, now of course, and it's only 6 years later now. I realize that the real privilege may have been seeing an ice covered North Pole, because it may well be that in a couple of generations' time, when you go to the North Pole in the summer, that it won't be covered in ice, and the flows, the ice flows, the processes that I studied may not be happening anymore, which is kind of a weird thing, because normally when you do science, you write a paper and that information sits there, it's going to be useful at some point, but it's very weird to study something and perhaps to be saying, well, I saw this, but in 20 years time this is never going to happen anymore. That's kind of a weird thing anyway. But yes, so that expedition, being in the silence of that world, and seeing, you can sort of imagine yourself on top of the world, watching the Earth's machinery turn around you. And the ice flows, big ice flows they're like ambush predators. I have filmed with alligators for the BBC, which I don't recommend. And the thing about alligators, so as the presenter of these TV documentaries, I have to be facing the camera, and that means for the benefit of the audience, the alligators have to be behind me, right? So I would say, I was sitting on a little island, and the cameraman is across the island, and the alligators are behind me, and I would say a piece, and they would kind of reset and say, oh, well, we nearly got it right, we're just going to do this again. And while they were saying that, I would look behind me, and then I would have to talk again. And every time I looked behind me, there were more alligators, and they were coming in closer, but I never saw one move. And yet every time I looked, they were doing something different. And the ice at the North Pole is like that. You never see it move, but every time you look, it's different. And that feeling of being like, you feel very small and vulnerable because you are. And that, in fact, on the final day of that expedition, I had brought in my scientific equipment on the second to last day. My colleagues left them out for one more day, and they came back, and this equipment had been there for a month on the same ice flow. And the last morning, the ship said that morning, we can't see it anymore. And they went out, and the ice flow had just, two ice flows had come together, and they just crushed everything. And it had happened without anyone on the ship a kilometer away knowing. No one could have done anything about it. We were lucky that no one was there. And their equipment had just vanished. That was it. There was no getting it back. They found some splinters of wood, I think, in the pile of ice. And I had my camera back, so I was very happy. But it was a reminder that, it's very easy to feel comfortable in that environment. It's very easy to walk about on an ice floe and go, oh, well, I'm just going for a walk on a piece of ice on top of the ocean. This is a perfectly normal thing to do. But you are extremely vulnerable, and that environment can turn at a moment's notice. And then you're in a very dangerous position. And so I think that, and of course it's to some extent it's always like that, but it was particularly visible. And so that was it was a huge privilege to work in that environment. Yeah. I mean, then the big waves and all that. Normally I study storms, so it was also calm. That was quite nice.
Yeah, I think that's a great answer. And like you said, maybe there's something else to it once you are at those poles, that you know the fact that, let's see how many decades to this, maybe it doesn't exist anymore in the same format as it is today. So based on the research and the book, because you have done an amazing job to explain the mechanics and how everything works, but with that knowledge base, what do you think are some of the most important new questions to ask? Because there's so many stories going around. Obviously, a lot of it is related to climate and weather and temperature. But do you see anything from your research that makes us want to ask new questions and do new research to truly understand what we are getting ahead? Or is that very difficult to know?
So there are, I mean, there's always new questions in research. And in the ocean, actually, the biggest questions are still the most basic ones, which is, well, especially one in particular, which is how does the energy move around? So the energy in the ocean is either heat or there's some movement energy, there's water flow and water moving around. And it's a slightly technical point. It makes more sense after someone's read the book, I hope. But how that energy is distributed around the ocean, inside the ocean, is really important. And the reason it's important is not just about temperature, it's because energy can mix the ocean up. So the ocean has layers, and if you have energy, you can mix those layers up, and that effectively lets things move up and down in the water column. And so there are one of the biggest open questions in oceanography is that technical one. It's how does the energy move? Because we know the Earth is that the ocean is this enormous reservoir of energy on Earth, but we can't see exactly where it all is, and we're still trying to understand the details of how the little bits move around. Whether it's a small number of big mechanisms that are responsible for moving the energy around, or whether it's just lots of little different things that move energy up and down. So there's some technical questions that oceanography has like that. And of course, they're important for the weather and things up on land, because if the ocean moves energy downwards, then it moves it away from the surface. And it's the surface temperature that generally matters for us. And then, of course, there are big questions about how the ocean will drive the climate in the future, because the climate, the weather of Earth is largely set by energy that comes from the ocean. And if it changes, then our weather patterns will change. And so we need to understand the processes going on underneath the surface to understand, because we just sort of see the flat top of the engine where there's all these three-dimensional processes turning underneath. So these questions about how exactly the engine will turn in the future, how exactly the water is going to move in the future, and what kind of energy, where it's going to move energy around to and from, those are very big questions. And we have some outline answers, but we don't have all the details. And part of the reason for that, it's not that we're not working hard on it. It's that every year you only get 1 year of data, right? It's the ocean the engine flows slightly differently every year, but you can only measure 1 year at a time. So when we only started measuring some of the details of the North Atlantic, for example, 20 or 25 years ago. So we've only got 25 years of data. We can't collect any extra years. And so to understand the difference between a slow trend, which is all going in one direction, and perhaps the slow natural variation where something might go up and then go down and then go up, we haven't got very many years to distinguish between sort of slow oscillations and a trend in one direction. And so, we're working on it, and we can be clever with how we use, so that the seafloor can act like a kind of library of the past, and we can look at that to see what's happened. But we have the problem that things are changing very quickly, but we don't have enough years of data to study all the details. And so it's a tricky bit of detective work, but there are big questions still to answer.
Do you feel like there's still huge discoveries to be made in how the ocean works, and also maybe related to how we as humans going to generate enough energy for our population? Because that's maybe like the biggest question you get all the time in financial news and energy news, and everything that surrounds humans is about how we're going to power all this energy that is going to be in demand for decades ahead. Do you think like ocean is going to give us the biggest answer? Because we're already trying a lot to use the waves and the winds. And do you feel like we can do some new discoveries, or are we just going to harness on existing solutions, and that we have done the most of the discoveries related to physics and chemistry and those solutions we use today?
I think when it comes to energy solutions, I think we know the basic physics that's going to help us with that. And so, you know, there is an enormous amount of energy flowing around the natural system. And of course, that's what we tap into when we take wind energy or solar energy. We just extract it from, you know, it's kind of flowing through the Earth system before it gets radiated away into space. Because we never really talk about that, you know, energy arrives on Earth from the sun and it hangs around for a bit, and then eventually it flows away. And so we're just kind of holding on to it for a little while, and it trickles through the weather and through life and all that kind of thing. And we're just kind of tapping into it along the way. And so I don't think there's any doubt that, I mean, certainly where we are in Northern Europe, you know, Norway and Britain, there's no question that wind energy we are perfectly set up for wind energy. We're in the perfect place. You know, different areas of the globe have different local energy sources. Well, ours is the wind, and there's no question about that. And of course, you know, Norway has hydropower as well. But when it comes to how the extra things, you know, there's only so many dams you can build. We are very perfectly set up for wind. And so I think energy from the ocean, the problem with energy in the ocean, and this applies to waves and tides and things to do with temperature, is that it's kind of dilute. So it's not that energy isn't there, but in order to extract energy, you need there to be a difference. So for example, if you have you know, just in your kitchen, you have a pan of hot water and a pan of cold water, there's a temperature difference between them. And so as energy flows from one to the other, you can kind of catch it on its way past. So that energy is usable energy. The energy that's in the hot water is usable because it wants to flow somewhere. There's a difference, and so you can extract it, so it becomes useful. But once you mix those two pots of water together, the total amount of energy is exactly the same, but you can't get it to do anything because there's no difference anymore. And so the problem with the energy in the ocean itself is that it's kind of dilute. It's kind of low level energy. It's the same, mostly the same everywhere. And so it's difficult to get much energy out of it in a very efficient way. You know, and of course, something like the equivalent of a ground source heat pump, if there's a difference between the temperature of the water and the temperature of the air, you can run a heat pump off that. But if you're on land, you don't want to heat things out in the middle of the ocean. You want to heat things on land, and you might as well use the ground. So the problem with energy in the ocean is there is a lot of it, but it's low level and dilute. And so it's not super useful. You know, tidal energy is only useful near the coasts in some very specific places. Wave energy, again, it's kind of dilute. It's, you know, it's hard to get it. You have to put machines in salt water, which they don't like. You have to maintain them, which is hard and expensive. And you need to, it's basically, you need to put a lot of things in the ocean to do it. You know, you have to put things in the way, which is going to affect ecology. And so the ocean, I don't think the ocean itself is not ever going to be an efficient source of energy in most parts of the world. There are a small number of exceptions, which are tropical islands. But you know, the wind and the solar is where those are the things that we, even in Norway, you know, solar energy, these are the things that are really going to offer us. That's where the big numbers are. That's where the big usable energy is. And I don't think the ocean is going to be that big a contributor.
Yeah.
Apart from offshore wind, you know, if you put a floating wind turbine, fine, but that's wind energy. It's not ocean energy.
Yeah. No, I think that's a perfect summary. So just some final questions. I mean, early on we figured out that you didn't really have heroes and sort of big role models, but I'm pretty sure many people look up to you. And I've heard you talk about sort of your way of looking at building an interesting career. And I think, you know, obviously the one part of the equation is to work super hard and be passionate about it. But you also had another point that I would like to ask you about, because we talked a bit about it in the start, but you said that you are very open to trying a lot of different ideas and projects without having that transactional mindset. So maybe just to, you know, summarize on that as well, because it seems like for you, that's been a huge part of the career you've carved out, that you've been so open-minded. Is that sort of like the main principle to have when you're young and starting out?
If you look back, you know, I give talks to students and things, and they all say, how did you arrive where you are? And I'm like, there wasn't a plan. I just took opportunities, and I think it's the attitude that gets you places. And if you look, almost everything I've done that is interesting it started in some place a thing that I wasn't supposed to do. It started from an informal thing, or I was just helping someone out. Um, I just gave something a go, just because I could. None of it would have come from the sort of the spine of what I've done is quite a traditional path. I went to university, I got a job, I did. The backbone is quite traditional, but all the way along the way, I just took opportunities to do other things. Actually, at the weekend, a week and a half ago, I learned to ride a penny farthing, which is a very old find of early in the early history of bicycles. Before there were bicycles as we recognise now, there were some that had a very, very big front wheel and a very small back wheel, and we call them a penny farthing in the UK. And it's an extraordinary bike. It's got no gears. The pedals are directly connected to this massive front wheel. You're sitting right on top of it. It's a completely silly thing to do, right? It's an enormous amount of fun. I highly encourage anyone who goes anywhere near a penny farthing to try riding one. And that will probably never be any use to me, but it was fun and I met some interesting people, and maybe some interesting things will come from it. But it's that kind of attitude where you might as well just do an interesting thing, and at the very least it will take you to interesting people. And to be open-minded about trying things just because they're fun and interesting, the world's changing, and it's very hard to predict now, I think, for young people now, to predict what kind of skills are you going to need to have a job in 15 years time. It's really not clear, but some things are. And being a good team player, being a good collaborator, being someone who's flexible, being able to experiment and work out how experiment more generally, not in a scientific way, that sort of flexibility, that is clearly going to be critical, and you only get that by trying it. And the thing is, it doesn't really matter what you practice on, so you might as well just practice on doing something new, and helping someone out and trying something, because what's the downside, really?
I think that's the perfect way of ending this conversation, Helen. So just the last part, where can people follow your work? What is, like, you're quite active on different platforms. So if people are interested to learn more about your work, where should they go?
Yeah, so I left Twitter, but I'm on everything else. So Instagram, LinkedIn, Mastodon, Blue Sky, Threads. And I have a website that is updated at least some of the time. So yeah, I guess those are the places to find out. And the website is www.helenczerski.net. But basically, if you search for Helen and Bubbles, you find me.
Yes, that's perfect. Okay, Helen, thank you so much for taking the time. It was a privilege to have you on.
Thank you for having me. It's been great to talk to you.